Boulders of giants.
So, yeah, just kind of rehashing some of the observables we talked about before, radiative recombination, and then some on non-radiative, how to get your photoluminescence in, some exploratory ideas for computing transient absorption for the excited state. And so everything, the most competitive aspects of our research is towards excited states. So you get an excited state somehow. So imagine this is an atom. You photo-excite it, you get an atom in a non-equilibrium spot. It's going to want to get back to equilibrium eventually. And there are multiple pathways to do that. So it could emit light to get back down to E1, or it could emit heat if it was in a crystal to get back to equilibrium, or it could also just transfer to something else too if it was coupled. And so you start with this picture, what are the ways that it can recombine? So the first person to kind of think about this was Einstein. He was probably just doing his usual thing, sitting around smoking his pipe and just debating with people all day long and thinking about thermodynamics a lot. But he eventually used a bunch of thermodynamic arguments to get to this expression. So our radiative rate is, we say it's equal to the Einstein coefficient. So this is the A that was in Kevin's presentation. And for specifically for luminescence, it usually comes from the HOMO-LUMO gap. So I just specify HOMO-LUMO for the indices. And then basically turns out to be a bunch of constants, except here transition energy, degeneracy of your states, and then he left it that this one term where it's the probability of transition. And at the time, like, people didn't really know what this probability of transition was. They just called it oscillator strength. And next slide I'll go over how that was figured out. But essentially, for everything we compute with our oscillator scripts, you can get your transition energy from the transition energy and the oscillator strength from the OS strength file that we generate. So if you get those two observables, you can in principle just calculate this rate if you just get a spreadsheet, plug in all the other numerical values in.
So oscillator strength, if it is a favorable emission, is of the order of 1.
Or if you normalize it, yes.
And what is the order of magnitude for the rest of the factor?
Oh.
If it is like yellow light to electron volt transition, is there like rough number? Is it like 1,000, 10 minus third?
So generally, your radiative rates for systems that we deal with a lot will be on the order of inverse nanoseconds, or it'll be on the time scale of nanoseconds. So yeah, inverse nanoseconds.
So if you're measuring in nanoseconds, then oscillator strength is about 1, and all other factors are 10 to the minus 9. Or if we are in nanoseconds, then of the order of 1.
Mm-hmm.
Okay.
I guess.
Good.
Yeah.
And also here we need to consider the degeneracy of the states.
Yes. So if for some reason your LUMO, like if you had, well, if you think about this picture here, so if you had two states only going to 1, you're kind of competing with another state, so you have a factor of a half less probability of that transition occurring.
And if it is goes from 1 to 2?
Yeah, you have more options, so it's more likely to happen.
Mm.
But most of the things we calculate, this term just evens out, or it's a wash. It's usually 2 over, the stuff I deal with, it's 2 over 2. 2 lowest energy and 2 LUMO states. And so the next slide isn't really informative, but it kind of describes where the oscillator strength term comes from. So this guy is Paul Dirac, and he was one of the first people to try to mix electromagnetic waves with quantum states. And then he did, you might have gone over in class time-dependent perturbation theory, but if you take the quantum classes, you'll see a little bit of it. But eventually he figured out that strange probability term in Einstein's equation just came out to this term, which is essentially a Fermi golden rule rate, which he actually discovered, but he named it after Fermi because he's modest or something. But then, yeah, he figured out that the probability of the optical transition comes from the transition dipole operator.
And this first equation denominator nu sub HO minus LU, it is the same term E2 minus E1 that Dan was asking about.
Yeah, it's essentially transition energy.
Should be some mu, I assume, is frequency.
Yeah, so it's frequency. So if you play with the H bar terms, you can just turn it into straight
If
energy.
you multiply and divide it by H bar,
Yeah.
then you get transition energies and energy, and then H bar squared in the
Okay, here it should be some energy conserving delta function.
So this is just one possible transition. So it's the
Assume that you have resonance set up. So you have atom with a transition frequency, given transition frequency, and given line that is exactly Q.
Oh, this is not rate.
right. Yeah, this is just the probability.
So this is not Fermi golden.
Well, Fermi golden rule will be like cross section or absorption rate.
Yeah.
And here is simplified to resonance condition.
So it's just dimensionless.
Yes. And so that covers just the brief background on radiative recombination. And so the other possible ways, if you have like an electron in a crystal, which is like a solid state, which is like pretty much all of us are dealing with for our research, is they can exchange energy with each other. So if you have an electron that's not in equilibrium, it can emit a phonon to get back down to equilibrium. And this picture is a guy named John Tully. He wasn't the first person to discover non-radiative recombination or non-adiabatic couplings necessarily, but he was just the first to try to implement it into molecular dynamics. And basically, he was the first person to do like all the simulations that we did, but in a different form. So, yeah, what describes that exchanging of energy is essentially the non-adiabatic coupling term that we've seen a lot in meetings. And so, practically, so when we convert the non-adiabatic couplings into the Redfield tensor, you can just look into the Redfield tensor for the specific homo-lumo transition you want, and that will just give you the rates of the non-radiative recombination, or an approximation of it anyway. So for my system, the homo-lumo gap was corresponding to these states, which you can find from your energy pop. So you go to energy pop, it'll tell you which, where in the matrix these states will be. So if you do RRR and then those states, it'll spit out a number at you. And this number will be in inverse femtoseconds. Just so when you're trying to convert it into something that makes sense with your radiative.
So how much this number will change if instead of 51 and 52, one would put like 52 and 53, which will be like Rumo and Rumo plus 1.
Right. Well, in this system will be about the same because of the degeneracy. But if you just look at
Okay, 52
Right.
and 54.
and so
You can finger right on the screen, I think.
And go to the next slide.
Yes, yes.
There we go. So this 51, 52 transition is like the across the band gap.
Mm-hmm.
Dimitri was asking if you looked at states in the conduction band, like how do these rates compare to this number?
Mm-hmm.
And something like this would be, I don't know, probably like at least 3 orders of magnitude. So it'd be more on like e to the minus 3 order of magnitude in inverse femtoseconds.
So 10 to the minus third
Right.
inverse femtoseconds.
Right. So it's a lot quicker. Maybe a lot quicker.
So this the number on the bottom, 8 times 10 to the minus 7, is about 1 times 10 to the minus 6 inverse femtoseconds, which will be about
1 nanosecond.
1 inverse nanosecond.
Right.
And the transitions inside the band will be about 1 inverse picosecond.
Mm-hmm.
Okay, yeah, thank you.
And so for when we make our figures, one way to keep all of them kind of internally consistent would be to choose the length or the non-radiative recombination time as the time scale for the dynamics that we do. And so this is just taking so K is the rate, so if you do the inverse, it gives you a time.
Mhm.
And then you just stick in the number that I got from the Redfield tensor. That gives you about 1 nanosecond for a time. So when you're making your blue figures at least, you want to have the time axis go to about roughly the same time as here. And for this figure, 1 nanosecond would be about 3 on our blue figure log scale, because it's kind of hidden in the background. But so just log a 1 nanosecond over 1 picosecond gives you 3. So that's how I arrived at that 3 number there. And so that way it makes sense. So if you had like a comparison model that you were doing, it would make sense to compare like the integrated PL between models. Because otherwise you could just run it for an arbitrary time, and it's kind of hard to make comparisons between models. You're trying to look at their emission capabilities anyway. And then to compute the actual photoluminescence quantum yield. So basically it's just the ratio of the rates of your radiative recombination divided by the sum of all the competing mechanisms. And so generally for simulations, we only worry about the radiative and non-radiative rates, but in principle, it could be, your model could be interacting with something else where the charge could transfer. So you'd also have to consider that as well.
Aaron, how would you modify this equation if you are looking for photoluminescence not from the terminal, not from HOMO-LUMO, but from highly excited state? If it will be how to assess what to give the photoluminescence from, let's say, HOMO to LUMO plus 40.
Right. You'd have to account for the rates of all the possible transitions. And so I guess I don't know all the permutations, but it would be the rate of whatever transition Dimitri was talking about, plus all the other hundreds of transitions.
So the rates of non-radiative cooling right now your K and R stands for recombination, because it's only one channel on the when we are on the lowest excitation column. And if we excite it higher up, one needs to add in the denominator rates for cooling from whatever LUMO plus 40 to LUMO and any intermediate states. And it will automatically make this quantum yield much smaller.
Yes. Yeah, that's fine. Yeah, hot luminescence usually doesn't have a good yield or even big signal. So.
So suppose my condition is from LUMO plus 3 to HOMO, then how many terms should I include it for the K and R?
From LUMO plus 3 to HOMO?
From LUMO plus 3 to HOMO.
So
to LUMO
then,
plus 3.
it'll be LUMO plus 3 to HOMO, LUMO plus 3 to LUMO plus 1, plus 2. And then, if you're just only looking for the efficiency of that one transition, I think that would be it. Yeah. So it'd be 4 terms, or 5.
Okay.
And then, I guess the maximum quantum yield you can have is 1 generally. Well, for the systems we look at anyway. If you're just thinking of radiative and non-radiative recombinations, it's generally 1. So you can have a range of values from 1 all the way down to, I guess in principle 0, but numerically you never see 0. So typical values you can see are, I've gotten some for models that are about 10 to the negative 8 to 10 to the minus 4. And those are kind of unusual systems. But if you're just looking for luminescence across the band gap, I've seen, for my models anyway, getting 50% quantum yields, which is pretty reasonable considering the size of the model that we deal with.
But if it will be like a couple of percent, like around 1%, it will still be something that one would be able to detect experimentally.
Anything? Oh, and then, so this is something new that Dimitri and I have been kind of talking about. So if you're not familiar with transient absorption, it's basically a way to pump probe experiments, what is another term that people call them. So basically you create an excited state and then you do laser pulses to track absorption signatures of the excited states as they cool to the band edges. So basically you can get an idea about the kinetics of the excited states. So it's kind of what we would base a lot of our, from our simulation, it's a natural comparison test to compare with people who do transient absorption. So yeah, information you can get is population dynamics, rates of population change, and long-lived intermediates. And from the calculations we do, we see all these things too. So it's, if you can find a good experimentalist who does transient absorption, it's be good for your career. Get some papers out of it. So, but with slight modifications to our code, specifically the time-resolved emission, you should basically, if you just disallow downward transitions, you look for upward transitions between the electron and the hole.
So swap the direction of the caret. Instead of J bigger than I, make J smaller than I.
Right. Right, and then you keep your oscillator strength the same, keep energy conserving term the same, and then your population term the same. So it's basically just playing with code a little bit until getting a reasonable figure or something that makes sense. And yeah, that's a work in progress. I can't even say that. I haven't really started working on it yet, but it's in the future plans.
Okay.
Those current brackets have some meaning?
No. Just to differentiate the parenthesis. So you just don't have
It's not anti-commutative. No.
So just difference.
Yes,
Density.
just difference.
Because if you have a fractional occupation, you would have half the spectral signature.
It's difference in range.
If your source and target states both are 50% occupied, then it is not able neither to emit nor to absorb.
Why?
Saying like if both are unoccupied, it cannot neither emit nor absorb. And if both are occupied, 100%, neither emit nor absorb.
But they're well, okay. If 100%, they're 100%.
Hmm?
They're both quite 100%. I agree.
If I want to emit my mass to your seat while you are sitting there, you will not allow me to do it because it is already occupied.
Okay.
Okay, let's please join me. Thank you.